Greetings and salutations, calculus students. I would like to, with this video, just show you examples of actually doing these. You took a lot of notes, you wrote down a lot of stuff, you've seen the formulas, but let's actually see what this looks like in action. So we're going to take a look at two problems, the first of which looks like this. I want to find the first three non-zero terms for a Taylor series of the function y equals sine of x. We'll do this at a couple different spots at x equals pi, but then we'll also compare it with a Maclaurin series, which will be centered at x equals 0. When I say the first three non-zero terms, that's going to be significant here because for a sine or a cosine function, a lot of the derivatives are equal to 0, so we end up not using all the terms. I wrote out all of my work and I just scanned it so you don't have to sit here and watch my hands as I'm writing this down, but this is what my work would look like if I'm doing this problem. My function is f of x equals sine of x. And so if I want to do a Maclaurin series, I'm centered at x equals 0. The Taylor series is at x equals pi. But for both of these, I'm doing the same thing. I'm saying, what is the value of the function at 0? Oh, shoot. I copied it down wrong. This should be at pi. Okay, I'm going to have to fix this. This should be f of pi. I believe I was thinking right when I did this. I just wasn't writing it correctly. These should all be at pi. And so the function itself is sine, the derivative is cosine, the second derivative is negative sine, the third derivative is, I lost track of where I was. Let's see, the third derivative, this is sine, cosine, negative cosine, sine, cosine, etc. And so I'm just plugging either 0 or pi into these two functions and getting these values. So sine of pi is 0, cosine of pi is -1, negative sine of pi is 0, etc. These coefficients, all of these zeros and ones and negative ones, they will be going into our formula as the nth derivative. For the Maclaurin series, it's x minus 0 or just x. And for the Taylor series, it'll be the derivative evaluated at pi, which I figured out already, and then x minus pi raised to the n power. So my Maclaurin series, I called it m of x to stand for Maclaurin. I've got a 0 term for the first term, but then I've got 1 times x to the 1 over 1 factorial minus 1 times x to the third over 3 factorial. There's a 0 term for the x to the fourth term, but then my fifth derivative was 1, so plus 1 x to the fifth over 5 factorial. When I'm trying to actually answer the question, what is sine of 3? The idea here is that I now have a series. It's a polynomial, or I guess not exactly a polynomial, but it's a three-term series, a fifth degree polynomial, I guess I can call it that is approximately equal to sine. So if I plug in 3, it's giving me an estimate for what sine of 3 is. Now, it turns out that this one's not great. The actual value of sine of 3 is not exactly this. Well, we'll take a look at this graphically. Actually, why don't we just go ahead and do that right away? Let's see, I've got to get up my Desmos window here. So here's what sine actually looks like. And what we just did is we have a Maclaurin series. The first term was just y equals x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And I've got it in sigma notation here, so it's kind of messy. But this is what we just plugged 3 into. And you can see when I plug 3 into this, I got a value, it was a little bigger than 0.5 something. And we can see that there's some significant difference there. It's not a great approximation. Over here, it's wonderful. Centering at 0, it looks really nice. But the farther we get away, the worse it gets. So let's take a look at the corresponding Taylor series. The work I'm going to do is the same. Remember, the coefficients I found were 0, -1, 0, +1, 0, and -1. And so when I plug these into the formula for Taylor series, those will be my coefficients. It'll be x minus pi to whatever power over whatever factorial. But everything else is going to look pretty similar. There's my -1, x minus pi to the first power over 1. Next coefficient was +1, x minus pi cubed over 3 factorial. Next coefficient was -1, x minus pi to the fifth over 5 factorial. And so when I plug 3 into this, I'm saying that this Taylor series is a good approximation for sine of x. So if I'm trying to find sine of 3, this should be, well, pretty good. And when I plug in 3, I just plug this in my calculator. I got about 0.1411, which is pretty good. And so if I look at this graphically, here's my Taylor series. And again, I'm centering this one at pi. So right here is the center of this Taylor series. This is, I suppose this is x minus pi to the first power. Sorry, negative x minus pi to the first power plus x minus pi to the third over 3 factorial minus x minus pi to the 5 over 5 factorial. This one centered at pi is giving us a much better approximation at x equals 3. In fact, to 4 significant figures, I think they were exactly the same. Now, if I want to estimate sine of 0, this one's not very good. So there we go. That's using a Taylor and a Maclaurin series to estimate sine of 3. Both of these are decent. Actually, let's put them both on the same graph. So the blue graph that's coming through, that one is the one centered at 0. The green graph is the one that is centered at pi. And if I add a few more terms, we'll see that they're both pretty good as long as we can see them in my window. I'll have to zoom out to see how they're different from each other. The green one is fitting really nicely for a nice wide window. The blue one is also, but their centers are different. The blue one is centered at 0. The green one is centered at pi. And so we just see different ranges where these are good fits. Just out of curiosity, I'm going to send this up to the 20th term and see how far they go. And you can see that the interval of convergence for these things is it's pretty wide. In fact, it's all real numbers if you send this through the ratio test. But there we go. The second example I would like to take a look at is this. Estimate the square root of 120 degrees. Excuse me, 120. I'm not sure why I said degrees. What is the square root of 120 using a second degree Taylor series? Here's the work that I have to do for that. Same as I did for the sine function, except I actually had to write this out because I don't know the second derivative of the square root of x off the top of my head. So I have the function, the first derivative, and the second derivative. If I want to use a Taylor series, the next question is, where do I center it? For the example we just did, we were estimating sine of 3, so pi was a really nice number to have my center because pi is pretty close to 3, so something centered at pi is going to converge pretty quickly at x equals 3. So the question is, if I want to do this at 120, what's a number that I should plug in? What's a number reasonably close to 120 that I could have this thing centered? And a key idea here is that we've got lots of radicals, so it's convenient for us to choose a number that we can find the square root of easily, or the square root of cubed fairly easily. And so numbers that we could choose, I've gone through this. Actually, I did this 4 different times to show you the different levels of precision that we're going to get. For the first example, I just plugged in x equals 1. 1 is a number that's got an easy square root. If I have the square root of 1 to the third power, that's a really easy thing for me to plug in. And so if I plug 1 into my function, my first derivative, my second derivative, I get these 3 values. So 1 is my first coefficient, 1/2 is my second coefficient, and then negative 1/4 is my third coefficient. And then we see the rest of it, x minus 1 to the first over 1, x minus 1 to the second over 2. Now the problem with this, it was really easy. X equals 1 is a nice easy number. I get a terrible approximation. This is an approximation of a square root, but it's centered very, very far away from where we want to actually evaluate it. So we get a number that doesn't even make any sense. I'll show you why we're getting a number that's that bad. So here we've got the square root function, y equals the square root of x, and the Taylor series that I just plugged in, centered at x equals 1, looks like this. It's great around x equals 1, But if I'm going to use this to approximate the radical, the square root of x at x equals 120, we can see uh, there's 120 over there, and this is nowhere close. At 1, it's fine, but far away from that, it is a hot mess. So let's try something that's a little bit closer. Now, maybe you know already, you're thinking of numbers that are perfect squares that I should be centering this at, but just to show you an arbitrary different number that's not great but not terrible, I chose x equals 49. Again, a number that I've got a nice easy square root of, and so I could plug this fairly easily. I had to plug this one in my calculator. I don't know off the top of my head the square root of 7 to the third power. I usually do when I get done teaching the exponent chapter, but right now it's just not on the top of my mind. So I plugged it in my calculator. That's wonderful. Um, and so I've got these coefficients, again, the 7, the 1/14th, and the negative 1 over 1,372. And so I can plug in 120 to this. This is approximately the square root of x. So the square root of 120, I plugged in 120 at these values. I got about 10.234, which actually isn't terrible. If I take a look at this graph, I'll maybe zoom out one more time. I'm going to change my window so this looks a little bit nicer. Let's go from 0 to 20 maybe. So this graph is centered at 49. So around 49, it looks great. At 120, it's not awful, but it's not really very good. Not a great estimate. Looks like we're off by about, let's see my vertical scale here. We're off by a little less than 1 or something like that, which not terrible, but not great. So let's try for a better approximation. And again, what kind of numbers could I plug in here? 1 was super easy, but too far away. 49 wasn't too bad. The next number I decided to plug in was 100. 100's a number. I've got nice perfect squares, or sorry, square roots. So I get fairly nice coefficients here, fairly nice for calculation. And so I plugged those in as my coefficients. I took a look at what this one looked like. And this one's starting to look pretty good. At x equals 100, it's great. At x equals 120, it's not too bad. Let's see. Here is x equals 100. This is where the center is. X equals 120. I don't know how well you guys can see this, but I just see a little bit of green peeking through from underneath this black graph. So pretty good, not perfect, but pretty good. The value I get when I plugged in 120 was about 10.95, which is within about 5/1000ths of the actual answer, which that's pretty darn good. But maybe you're a step ahead of me on this one, considering numbers that we could plug in. 1 was easy but terrible. 49 was not too bad, but not too good. 100 was not terrible for actual calculations, but the number 121 is going to be really, really good. We get a little bit messy coefficients, but that's the trade-off that we're going to make here. Fairly easy to find square roots of 121. This coefficient, again, I had to plug into my calculator. I didn't know off the top of my head what the cube of the square root of 121 was. And then I had to also multiply by 4 to get that coefficient. But there we go. I've got a really nice approximation for the square root function centered at 121. So when I plugged in 120, I got almost exactly the correct value for the square root of 120. I'll show you graphically what this looks like, though it looks pretty similar to what we just saw. This one is centered at 121, and so 120 is very, very close. And like I said, the value that we got, I don't remember exactly what it was, but it was almost exactly the square root of 120. If you're wondering what the point of all this is one of those things that I would probably be spending a lot more time talking about if we were together in class. Um, I guess the best way for me to efficiently and quickly say this is that in the programming of calculators, in programming of general programs, exact values don't work very well. It's hard to tell a computer to do the square root of 120 There's programs, and how these programs work is basically by doing the stuff that we're doing right now. And I wish I could say a lot more about it, but I think this video is probably long enough as it is. I will mention again, um, and maybe you want to do this. There is a video in the AP Central folder that I made that goes through Taylor series and approximations and stuff that we're doing. Check that one out. I'm going to do a better job on my next video of making sure I'll put that at the front of the video instead of the back end. But check those out. As always, if you've got questions, if you've got concerns, if you would like to Zoom sometime, I don't know if you guys have seen, but they've got a schedule for us at this point. If we want to do another Zoom conference, well, I mean, we can do one whenever we want. But if we want to have a time where I know that nobody will have conflicts, looks like Thursday afternoon, 2:30 to 3:30 is a time that we could do a Zoom, so we could get together and talk about this stuff. Otherwise, keep working on this section. Take a look at the assignment. I don't think I have anything else that I need to do in this section, but there are a couple things that I do want to do before we get done with this one. Let's talk on Thursday about when tests and quizzes and stuff like that and how that's going to work. But in the meantime, work on this stuff. Good luck with this stuff. Please let me know if you have any questions, and I will see you some other time. Bye.